All right, so get this. We're diving deep today into the world of springs.
Springs.
Yeah, you know those things that make trampolines bouncy and slinkies wiggle?
Yeah, and actually it's not just about those familiar coils, the
Mhm.
physics of springs. Uh, they're everywhere,
Right.
from the suspension in your car to, believe it or not, the structure of DNA.
Wait, DNA acts like a spring.
It's true.
I never would have guessed that.
Yeah, the double helix structure, it's like this tightly wound coil, and it stores and releases genetic information with amazing efficiency. But before we get too far ahead of ourselves, let's start with some of the basics.
Okay, back to Springs 101 then. And we're exploring this through a resource called the Hooke's Law model.
Right?
It's like a virtual lab where you can play with springs and see how they behave.
Exactly. It's from Pithy Interactive Simulations, and it's designed to help you grasp some key physics concepts, force, spring, constant displacement, and potential energy.
Okay, all the fun stuff.
All that fun stuff.
So break it down for me when we talk about force with a spring. What exactly are we talking about?
Think of it as any push or pull. So when you stretch a rubber band, you're applying a force. Same thing, when you push down on a mattress, you're exerting force on all those springs.
Okay, got it. Force is the action. So what about spring constant? That sounds a little more technical.
It's simpler than it sounds. Spring constant is basically a measure of how stiff a spring is. So a slinky, for example, has a low spring constant. It's easy to stretch.
Yeah.
But the heavy-duty springs in your car suspension, they have a high spring constant. Takes a lot more force to move them even a little.
So high spring constant equals a tough spring. Makes sense.
Yeah.
Now throw displacement at me. What's that all about?
Just a fancy way of saying how far a spring is stretched or compressed from its resting position. So if you pull a rubber band back an inch, that's your displacement.
Okay, force is the action spring constant, is the stiffness displacement, is how far it moves.
Yeah.
Now, hit me with potential energy.
Mm-hmm.
Isn't that what I need to get through Mondays?
Well, it's definitely a kind of energy. Potential energy is energy that's stored up, ready to be released. So when you stretch that rubber band, you're loading it up with potential energy let go. And bam, that energy turns into motion.
Like a slingshot ready to fire. The more you stretch it, the more potential energy
Exactly.
waiting to be unleashed.
And that's a key relationship that Hooke's law helps us understand. The amount of potential energy stored in a spring is directly related to how far you stretch or compress it, that displacement we talked about, and the spring constant.
So a stiff spring stretched a long way, that's a recipe for a lot of potential energy.
It's like pulling back a really strong bow and arrow. You're storing up a lot of energy that's just waiting to be released.
Okay, I think I'm starting to get the basics here, but I'm curious, what can you actually do with the Hooke's Law model?
One of the coolest things is that you can experiment with linking springs together.
Oh.
You can connect them end to end, we call that series, or side by side, which is parallel.
Interesting. Does that change how they behave? Do they turn into some kind of super spring?
Not quite a super spring, but it definitely affects their overall stiffness and how much force is needed to stretch them.
Okay.
Think of series springs like adding resistors in an electrical circuit. The total resistance increases.
So like two weak springs linked together might end up acting like one strong spring?
Exactly. And it works the opposite way with parallel springs. The more you add side by side, the harder it becomes to compress them, like trying to squish a whole bag of marshmallows at once.
This is making me look at everyday objects in a whole new light. I bet springs are hiding everywhere, doing all sorts of cool things.
You're absolutely right, and we'll explore some of those real-world applications in just a bit. But first, let's take a quick look at the specific learning goals you could achieve by using this model. So those learning goals are really going to help us dive deeper into these concepts. But let's shift gears a bit and see how these principles play out in the real world.
Yeah, let's bring those springs to life. I'm ready to see them in action.
Okay, great. So let's start with something you probably experience every day, your car.
My car uses springs. I never would have thought about that.
Your car's suspension system.
Really?
It's a prime example of springs in action. Every time you hit a bump or a pothole, those springs are compressing and releasing, smoothing out the ride, absorbing shocks. Without springs, your car would be bouncing all over the place.
Wow, it's like my car is constantly doing physics experiments while I'm driving.
Exactly. And it's not just cars. Think about trampolines. They're essentially giant spring systems designed to convert your downward motion into upward motion, giving you that exhilarating bounce.
Okay, trampolines are definitely all about springiness, but what about something a little less obvious?
How about the spring-like properties of muscles and tendons?
Hmm.
They play a huge role in the efficient movement of animals every time you take a step. Your Achilles tendon stretches and recoils like a spring, storing and releasing energy to propel you forward. It's a brilliant example of nature's design.
That's incredible. So it's not just about bouncy toys and car parts. Springs are fundamental to how we move and interact with the world.
Precisely. And it goes even deeper than that. Remember how we talked about DNA having a spring-like structure?
Yeah, that blew my mind a little bit.
Well, that coiled structure, it's not just a coincidence. It allows DNA to store and release genetic information with incredible efficiency. And when cells divide, the DNA strands actually unwind and replicate in a process that's directly related to their springy nature.
Okay, now I'm really seeing springs everywhere. It's like they're this hidden force driving all sorts of processes, big and small.
You're getting it. And we
Uh,
haven't even scratched the surface of all the fields where springs are essential. They're crucial in architecture, where they can help buildings withstand earthquakes and adapt to changing conditions. They're found in musical instruments, controlling the delicate movements of hammers and strings to create beautiful sounds.
So springs are the unsung heroes of everything from skyscrapers to symphonies.
You could say that. And the more we understand about the physics of springs, the more we can appreciate the ingenuity of their applications both in nature and in the technologies we create.
This is all starting to feel very interconnected. Like springs are this tiny window into the fundamental principles that govern the universe.
That's a great way to put it. Springs might seem simple, but they embody some profound concepts that extend far beyond those coiled pieces of metal.
Okay, I'm officially hooked on springs, but I do have one question. Are there any downsides to using springs? Do they ever, spring a leak, so to speak?
That's a good question, and you're right to point out that springs, like any technology, have their limitations. One of the main challenges is that springs can wear out over time, especially if they're subjected to repeated stress.
Yeah, like an old trampoline that's lost its bounce,
Yeah.
or a squeaky door hinge that needs some WD-40.
Exactly, as springs age, they can lose their elasticity or become brittle, which can affect their performance and even lead to failure.
So it's not all sunshine and rainbows in the world of springs.
Yeah.
Are there any other drawbacks we should be aware of?
Well, another potential issue is noise springs can sometimes be squeaky or rattly, especially if they're not properly lubricated or if they're vibrating at a certain frequency. And of course, size and weight can be a factor for certain applications like aerospace engineering, or microelectronic springs might be too bulky or heavy.
So while springs are incredibly versatile, engineers and designers have to carefully consider their limitations and choose the right spring for the job. It sounds like there's a whole science behind spring design.
You're absolutely right. It's a fascinating field that combines physics, materials, science, and engineering to create springs that meet specific performance requirements.
Wow, I'm learning so much. But I have to ask, we've talked a lot about how springs work at a macro level, but what's happening at a microscopic level that gives springs their springiness?
That's a great question. Ultimately, the springiness of a spring comes down to the electromagnetic forces between the atoms that make up the spring material.
Okay, now we're getting down to the nitty-gritty. Can
Uh,
you elaborate on that a bit?
I imagine each atom as a tiny magnet. When you stretch or compress a spring, you're changing the distances between these atomic magnets. When you pull them apart, they want to snap back together. When you push them closer, they repel each other.
So the springiness we observe is really just a manifestation of these tiny electromagnetic interactions happening at the atomic level. It's
Well,
like zooming in on a spring and seeing a whole universe of forces at play.
that's a great analogy, and it highlights a fundamental principle of physics. The same laws that govern the behavior of atoms also govern the behavior of everyday objects.
This is all starting to feel very interconnected. It's like springs are a microcosm of the universe, reflecting these fundamental forces that shape everything around us.
You're right on the mark, and in the next part of our deep dive, we're going to explore how those springy insights connect to even broader themes in science and technology.
I can't wait to see where this stringy journey takes us next. It sounds like we're about to springboard into a whole new level of understanding. All right, we're back and ready to wrap up our springy adventure. My mind is still buzzing from those atomic level insights.
It is pretty mind-blowing, right?
Yeah, it is.
How something so simple can connect to such profound concepts. And speaking of connections, I think it's time we explored one of the most intriguing aspects of springs, oscillation.
Oscillation like a back and forth motion?
Exactly. Springs, they're the masters of oscillation, constantly storing and releasing energy, bouncing back and forth in this rhythmic dance.
Mhm.
We see it not just in mechanical systems like pendulums and vibrating strings, but also in countless natural phenomena.
Okay, give me some examples. I want to see this oscillation idea in action.
Well, for starters, think about light and sound. They travel in waves, which are essentially oscillations of energy.
Okay.
Light waves oscillate at these incredibly high frequencies, which is why we can see different colors. Sound waves oscillate at lower frequencies, and that creates the sounds that we hear.
So the music I'm listening to, the colors I see, it's all just different forms of oscillation.
Pretty much. And it doesn't stop there. The Earth's rotation that creates the cycles of day and night, this grand oscillation that governs life on our planet, even the planets in our solar system, they oscillate in orbits around the sun.
Okay, so I'm starting to see a pattern here. It's like oscillation is this hidden rhythm of the universe playing out on scales both large and small.
Exactly. And springs, with their inherent tendency to oscillate, they provide this tangible way to understand this fundamental principle. By studying how springs behave, we can gain insights into the nature of oscillation itself.
This is really making me think, but let's bring it back down to Earth for a
Yeah.
moment. How does understanding oscillation actually help us in practical ways?
Well, for one thing, it's essential for designing countless technologies. Radios, they rely on the oscillation of electromagnetic waves to transmit and receive signals. Clocks, they use the regular oscillations of a pendulum or a quartz crystal to keep time.
So our ability to communicate, navigate, and even measure time hinges on our grasp of oscillation.
It does, and it's not just human-made technology. The beating of our hearts, the ebb and flow of tides, these are all driven by principles of oscillation. It's a concept that's deeply woven into the fabric of life and the universe itself.
Wow. We've gone from simple springs to the grand rhythms of the cosmos.
Yeah.
It's amazing how these concepts are all interconnected.
Yeah.
Is there anything else we can learn from our deep dive into the world of springs?
I think there's one more key takeaway: resilience.
Resilience, like bouncing back from challenges.
Exactly. Springs, they're inherently resilient. You can stretch them, compress them, bend them, but they always strive to return to their original shape.
Like those springs are a metaphor for how we can face challenges and setbacks in life.
Exactly. We all experience difficulties, but just like a spring bounces back from being compressed, we too have that inner strength to adapt, overcome obstacles, and even grow stronger from those experiences.
That's a really powerful thought.
Yeah.
It's like those springs are offering a little lesson in resilience, reminding us that we can always bounce back.
Precisely so. The next time you encounter a spring, take a moment to appreciate its simple beauty and the profound lessons it holds. It's a reminder that even in the face of challenges, we have the potential to spring back stronger than before.
This deep dive has been an incredible journey. It's completely changed the way I see springs. They're not just mechanical devices, they're tiny teachers offering insights into physics, the universe, and even ourselves.
And remember, this is just the beginning of your exploration. The world is full of springs, just waiting to be discovered and understood.
Well said. And to our listeners, we encourage you to check out the Hooke's Law model. It's a fantastic free resource that lets you experience the principles we've discussed firsthand. And as you go about your day, keep an eye out for those hidden springs all around you. You might be surprised at how these simple yet powerful devices shape our world. Until next time, keep exploring, keep learning, and keep springing forward.